Okay, good afternoon, everyone. I think we'll get started. My name is Mike Seeley. I'm director of the Princeton Environmental Institute, and on behalf of PEI, as well as Civil and Environmental Engineering, I want to welcome you to this afternoon's seminar. We are indeed fortunate to have Professor Katul with us, who has appointments in the Nicholas School, as well as the Department of Civil and Environmental Engineering at Duke University. He has many accomplishments. I told him, with apologies, I will keep this brief. He has been editor and associate editor for a number of journals, including spending 4 years as editor-in-chief of one of the major journals in the field of hydrology called Advances in Water Resources. I should say that his position is the Theodore S. Coyley Professor of Hydrology and Micrometeorology. And that tells you a lot about his research fields, which span both hydrology and micrometeorology. He works oftentimes very near the land surface of the Earth, looking at the space involving soils, vegetation, and the local atmosphere, and considers many very interesting problems along that interface. He is very accomplished in terms of his research. He's received a number of awards. I'll start with one that I'm always impressed with, which is the Editor's Citation for Excellence in Refereeing by the AGU, which tells you that he's willing to spend a lot of time doing a job that we all know takes a lot of time to do it well, and for which you're almost never thanked in any real way, except the editor saying thank you for actually doing this. He received the McElwain Medal from the American Geophysical Union. If you don't know, that is the highest medal given out by the union for young researchers. It comes with fellowship in the AGU along with the medal. He later received the Hydrologic Sciences Award from the Hydrology section of the AGU, and this year he is either has received or is going to receive, let's say he is receiving, the Dalton Medal from the EGU, the European Geosciences Union. And that is a part of a much longer list of awards and accomplishments. So please join me in welcoming Katul for our seminar series.
Thank you all for having me here. It's always fun to come back and see everyone. They're not changing much except the color of the hair. This work that will be presented today is in collaboration with my colleague, Heping Liu, who spent some sabbatical at Duke University for a couple of months and really instigated the work on this problem, which is universal scaling law for gas transfer velocities across complex interfaces. So let's see how this works. Okay, so the significance of turbulent exchanges near interfaces, whether be it water or solids, on human health, ecosystem, and climate-related processes is not in dispute. There's no point in spending a lot of time justifying why we are working on this problem, but just to give some flavor of why it is relevant. There was a massive incident in about 1986 in Lake Nyos in Cameroon, where a major degassing of CO2 occurred and was responsible for killing more than 1,200 people. And that's basically one example where gas transfer turned out to be lethal because of volcanic activities below the lake, or so it was suspected. If you look at the climate-related processes, the applications of gas transfer theories near interfaces are also important. Just as a case study, if you look at the total CO2 emissions from inland waters, so this is about 2 petagrams of carbon per year. If you add about 0.6 petagrams of carbon per year that may come from methane emissions from peatlands, that gives a total number of about 2.6 petagrams of carbon per year. So that's roughly the emissions of CO2 from inland waters and methane from peatlands. If you look at the CO2 concentration in the atmosphere from year 2000 to year 2006, it's been growing by about 2 parts per million per year, which then would require a global source of about 4 petagrams of carbon per year. So that gives you a sense of how important the inland water is. Another application that is playing prominently both in agriculture and environmental engineering, particularly wastewater treatment, is the nitrous oxide emissions from wastewater treatment plants. There's been quite a bit of attention to that problem, also in fertilized agriculture, intensively fertilized agriculture, to the extent now that nitrous oxide is sometimes labeled as the new ozone enemy for reasons that have to do with the chemical composition and the destruction of ozone, but also for air quality purposes as well and climate change. So this is again a problem that deals with interfacial transfer processes, gas exchange near either a rough surface, such as the one that is here, or water interfaces, such as the one here. So having just briefly touched upon why this problem is of significance, the good thing is that if you're dealing with turbulent transport processes, there is no final solutions to these problems, only scratching the surface. And what we're going to try to do in this talk is to try to describe basically the efficiency of turbulence that is removing mass next to these types of interfaces. And that's primarily going to be the talk, is describing the mechanisms that would describe the efficiency of turbulence responsible for these types of transport processes. This problem is receiving, so to speak, a renaissance just because mass transfer studies across interfaces are actually being enriched by a large number of measurement techniques. Should I? Okay, maybe I come here.
I think the voice is a little bit low. Is everybody hearing okay? Okay, sorry to interrupt you.
So, okay, I'll try to come closer to the microphone. There has been a renaissance in studies of mass transfer studies across interfaces, primarily due to the fact that remote sensing technologies such as infrared cameras are proliferating, and they're able to provide unprecedented resolution in space-time measurements of temperature. Fiber optic cables now are doing, so to speak, miracles when it comes to studying interfaces as well. Stable isotopic techniques have improved dramatically to the extent that now they are able to tease apart sources and sinks or the origin of scalar material in the fluid. And the computational approaches that have been developing over the past 30 years for dealing with turbulence have improved dramatically, whether be it through subgrid scale modeling of large eddy simulations or even the direct numerical simulations, because near interfaces, almost the Reynolds number are sufficiently low to permit the DNS to be conducted. What seems to be lagging behind these experimental or simulation techniques are somewhat theoretical models that try to describe these types of mass transfer processes. And so the talk will be also dealing with some work on developing these types of exchange models with the premise that they're going to be phenomenological, not extremely rigorous. So instead of dealing with fluxes and concentrations, what we're going to do is work on a transfer velocity, and the transfer velocity, often referred to as the gas transfer velocity, is going to be defined as the flux divided by concentration difference. This concentration difference will be defined based on some surface value and some bulk value away from the surface. And the goal of this talk is to try to bring eddies into the description of the transfer velocities. After all, this whole approach is to try to describe turbulence, but it seems that the majority of the theories don't have eddies in them directly. So we will try to bring that into the picture. The earliest approaches that attempted to do that were based on surface renewal theories. This is one of the hallmark achievements of fluid mechanics and chemical engineering. Higby in 1935 started work on surface renewal, and then it proliferated over time. The two key results that are in use now in terms of bringing turbulence, at least explicitly, into gas transfer models are either attributed to Lamond and Scott in 1970, where they actually showed that this transfer velocity depends on the Schmidt number raised to some exponent to be discussed later, multiplied by the dissipation rate of turbulent kinetic energy multiplied by the viscosity of the fluid raised to the 1/4. 5 years before them, however, one of our own distinguished hydrologists, Wilfred Brutes, actually derived an expression that could be reformulated along the lines of Lamond and Scott, and we will touch upon that as well, where he actually showed that the transfer velocity of gas next to rough interfaces, this was during studies of evaporation from bare soil, is proportional to the square root of the molecular diffusion coefficient, multiplied by the friction velocity, which is dependent on the surface stress, raised to the 3/4, and then adjusted by a set of constants. Kv is the von Karman constant, Z0 is the momentum roughness height, and the viscosity of the fluid raised to the -1/4. it should not be a surprise that there is a minus 1/4 here, a 3/4 here, and a 1/4 here. We will show the connection between those in a minute. But these were the two key results. Now, what was surprising about these results is that when they were applied to varieties of surfaces, the scaling law, the 1/4 scaling law here, or the 3/4 scaling law here, appear to hold, and also the similarity coefficient that surface renewal schemes cannot predict easily, alpha in this case and A in this case, appear to be invariant or roughly constant, which was a surprise. Okay. So part of our goal then, when we try to bring eddies into the picture, is to show that the universal scaling that is originating from these expressions, and they were derived from surface renewal theories, meaning they make no contact with Navier-Stokes equations, can in fact be predicted from well-established theories of turbulence attributed to Kolmogorov's 1941 work when viscous cutoffs are adjusted for. And then we will also show that these gas transfer models appear to be insensitive to the renewal time distributions for a reason, because there are other mechanisms that can reproduce these types of scaling laws without having to invoke renewal schemes. And finally, we will show that the similarity constants, alpha and A, are independent from the specifics of the interfacial system based on the approach that we're going to propose. So it will show why these alpha and A tend to have universal values. So what's the problem that we're going to discuss? We're going to do two of them. One of them is from the water side. The other one is on the air rough surface side. On the water side, we're going to consider an air-water interface that is clean, no surfactants that are added that will alter the solubility of the gas in water. And that means that we're going to assume an equilibrium between the air side and the water side. That will be described by Henry's law or some Oswald solubility coefficient. So that means that the surface concentration is pretty much set by the air concentration. And then away from this interface, there will be a well-mixed region characterized by some bulk concentration CB. And of course, the region between the interface and this bulk region is where the action is and where we are going to try to describe the flux of gas either in or out from this region. And the transfer velocity is still defined in the same way, so we're going to consider this flux. Delta C then will be the difference between the surface concentration in the water side and the bulk concentration. So what is done in practice now to represent this mechanism is to use empirical formulations that link this type of water side gas transfer velocity to the mean velocity in the atmosphere at some reference height, often 10 meters. And so you find equations that are used now in climate models of the form K is A plus B U to the C, where U is the velocity in the air, not in the water, yeah? Raised to some power C. And the variations in the coefficient C goes from 1 to 2, so linear to quadratic. And A could be 0 to some big number like 2. And the mean velocity here is defined often at 10 meters, simply due to the fact that NSAP pre-analysis data provides you with mean velocities globally at 10 meters. So that's part of the reason why this reference height was selected. However, with these types of empirical approaches, if you want to see how well they describe data sets in reality, this is a graph taken from the book by Karman and Anna Rutgerson and many others, where they actually had the graph that showed the mean velocity on the x-axis in the atmosphere. This is wind speed. And the transfer velocity here normalized to a Schmidt number of 660 as a reference. And you could see that you could have almost linear. You could have more than quadratic variations. And what is done often in practice is to use some sort of an ensemble curve to all these types of data sets. And that ensemble curve makes its way into climate models, where you get something that looks like this, a transfer velocity globally that varies with the bulk velocity, that of course then can be determined from NSAP pre-analysis data across different regions of the world. And even with this type of approach, you see that this type of transfer velocity can go from 1.8 to 34.4. These are meters per day, but they're annual averages. This was a graph taken from Raymond's paper in 2013. And this is the sort of scheme that is used to assess the significance of inland water contribution, whether it be CO2 or methane, to the climate system. So can we do better than that, basically? Or at least try to explain why A, B, and C vary so much from basic principles. OK, so to do that, we mentioned already the paper by Lamond and Scott. That was an important paper. It's cited all over in the literature, especially the oceanography literature, and now more and more so in the inland water literature. It does suggest that the transfer velocity, the gas transfer velocity K, is some constant that is about 0.4. But some studies do report lower and higher values, but not many of them, multiplied by a Schmidt number that is typically defined as the viscosity of the fluid divided by the molecular diffusion coefficient, which for water is going to be much, much bigger than 1, because the water molecules tend to be packed together compared to air molecules, and hence to have gas diffuse through those water molecules, you have to wait very long, okay? Just because of the packing. And so the Schmidt number in water is, of course, much bigger than 1 compared to air. And nu here is the kinematic viscosity of water. dm is the molecular diffusion coefficient of the scalar C. And this quantity epsilon is known as the turbulent kinetic energy dissipation rate. This is on the water side. And n often so is determined as 1/2. And that seems to have some wide support empirically and theoretically. The paper by Lamond and Scott, which was published in 1970, labeled this approach as an eddy cell model of mass transfer into the surface of a turbulent liquid. Textbooks now call it actually the micro-eddy theory, and we shall see in a minute why. The reason it is called micro-eddy mixing is due to the fact that the term dissipation rate multiplied by the viscosity to the 1/4 is quite connected to the Kolmogorov velocity, and that is formed by a length scale that is known as the Kolmogorov length scale. This is the smallest length scale of turbulence, where there is a handshake between viscosity acting to dissipate turbulent kinetic energy and turbulence, basically. So really this is the transition between turbulence and basically the action of viscosity. A Kolmogorov time scale can also be formed by the same variable, dissipation rate and molecular viscosity. And of course, the Kolmogorov velocity can be formed also by the same variables. And if you really want to see why this length scale is so critical at the handshake between viscosity and turbulence, you could compute a microscale Reynolds number, which is formed by the Kolmogorov length scale and the Kolmogorov velocity, which would end up having a value of exactly 1, meaning that both processes, molecular processes and turbulent processes, are somewhat relevant. Okay, so this is the reason why this term comes up a lot, and that's what we're going to call this term for short, Kolmogorov velocity scale. How well does the surface renewal scheme of Lamond and Scott perform? This is a paper, an influential paper by Christoph Zappa, that showed the predictions from surface renewal theory on the x-axis versus measurements on the y-axis. The solid line that you see here is basically the expression 0.42 Schmidt number to the -1/2 multiplied by the Kolmogorov velocity. And while there is some scatter, the agreement is not that bad. A critique of this paper popped up as to how the dissipation rate is defined near interfaces. My limited experience with this is to simply say that if you look at the data sets that are coming out from the literature, where the dissipation rate was measured near interfaces, it appears that the dissipation rate is becoming independent of height. So as long as the measurements are done close to the interface, this may not be a big problem. The other thing is that the 1/4 power dampens a lot the error in the dissipation measurement. So if the error is a factor of 2 in your estimates of the dissipation, your gas transfer velocity may be off by 20%, which on this scale is hardly visible. Yeah, so actually the data sets came from a wide range of systems. It's from marine and aquatic systems. So it was inland and marine systems.
But not at high wind speed, right?
I know for a fact that Duck, North Carolina would have a high wind speed case, because that's in North Carolina. I think it samples a wide range of wind speed conditions. And perhaps some evidence for it is that you could see that the transfer velocity that they're getting varies by almost a factor of almost 2 decades. Exactly, because of waves. But that's the inland water, I think, is probably a little bit more stable. But still, I think the wind speeds are not trivial. Yeah. It's not very calm, let's say. It's not convective. Okay, so now that we have discussed briefly the work of Zappa and Lamond and Scott, let's go back to hydrology, which was actually the work of Wilfred Brutes in 1965, 5 years before them. Wilfred at the time just finished his PhD degree at UC Davis. He worked with Bill Pruitt. He saw the installations of the first lysimeters at UC Davis. These were huge lysimeters, 6 meters in diameter. This was on the cover of the talk. So when he started at Cornell, he was pretty much being thrusted by the work at Davis, and started looking at the topic of evaporation from bare soil as a molecular diffusion process into a turbulent atmosphere. And actually, I decided to put the abstract of Wilfred's paper because every time I'm stuck in terms of writing papers, I actually go back and read that abstract. So I thought it would be worth just reading those 4 sentences. It said, evaporation is analyzed as a phenomena of molecular diffusion from a large rough surface into random-lived internal scale turbulent eddies, which we are going to interpret as the Kolmogorov eddies. Okay? And that's how Brutes also interpreted them. The model is based on the principles of similarity and stochastic renewal. It is shown that evaporation is proportional to the 0.75 power of the friction velocity and the square root of the molecular diffusivity. This is in agreement with the available experimental data. And that's all that is said. Now, if you compare this type of writing style with the current papers, you miss this kind of writing style. Okay. So what did Brutes do in a nutshell? Brutes' derivation was quite elaborate. This was an 11-page paper. But the essential physics behind it is actually quite simple and quite intriguing. What Brutes considered is a rough surface, such as the one that is shown here. He took the momentum, he took basically the roughness out, replaced it with a momentum roughness height that is called Z0. And so now the surface is flattened, with of course, ondulations having a little bit more area, but to a leading order, those are gone, they are minor. And so you have now a surface that is flat, characterized by momentum roughness height. He assumed that the concentration near the surface is characterized by a surface value, whose value is dependent on the evaporating surface. So the water vapor concentration in this case would be high. And then as you go away from that evaporating surface, the concentration drops. And hence he characterized the concentration difference between the bulk region, which is a little bit away from the surface, and the surface region as delta C. Then he made the argument that parcels of air that are originating from this region make their way down to the region through a sweeping event, make contact with the surface. Once they make contact with the surface, the only way water vapor molecules can enter those parcels of air is through molecular diffusion. And that what happens is that as the parcel sits here, there is a diffusion front that is simply moving up into this parcel until an ejection event kicks this parcel out and it is immediately renewed. And of course, over a certain duration tau, the enrichment of that bulk concentration in that parcel will go up until the renewal event occurs, and then it will continue to go up again and again. And of course, it will go up more and more if the contact duration is longer. Now, one might criticize this model because typically at a given point, the renewal scheme is not continuous. Actually, there may be quiescent periods where nothing is happening. But in space-time, in fact, there may be a continual renewal mechanism. In other words, there is always a renewal process happening somewhere in the spatial domain. So at some level, Brutes' naive approximation may actually be better representing space-time rather than just a single point in time. So with this scheme, what was then suggested by Wilfred, going the wrong direction here, that from a physical perspective, and this is really simplifying Brutes' physics a lot, and of course we can do that now in hindsight, he didn't have that luxury. You could simplify the physics a lot by simply assuming that the instantaneous evaporation rate is the molecular diffusion coefficient multiplied by the concentration gradient at the surface, C equal to 0. And rather than go ahead and try to solve the diffusion equation with complex boundary conditions, one might make immediately the argument that the concentration gradient is characterized by some concentration difference divided by some characteristic length scale. This concentration difference can encode all the spatial information in the concentration gradient, and this length scale here simply reflects how long the diffusion front moved into the parcels of air. If you accept that sort of scaling argument, then the instantaneous evaporation rate must scale with the molecular diffusion multiplied by this concentration difference, divided by the square root of the molecular diffusion times the contact duration. That sets actually how far the diffusion front has moved into the parcels of air. The bigger tau, the contact duration, the bigger that distance is. Now, if you bring delta C to this side, we have the transfer velocity that is now instantaneous, and it varies with the contact time. And that contact time has to be positive, so the parcel has to make contact with the surface. And that turns out to scale as square root of the molecular diffusion divided by the contact duration. Now, of course, this is instantaneous, and tau is random, which is the essence of surface renewal schemes. So if you assume a probabilistic description for these contact durations, and Brutes assumed the simplest that you could think of, which is an exponential distribution, and then he further made the critical assumption that the parameter of the exponential distribution, so the exponential distribution has really one parameter, is proportional to the Kolmogorov timescale. So he assumed that the mean contact duration at the interface are the inner scale that he labeled in the abstract, which is the Kolmogorov timescale. And the Kolmogorov timescale is formed by the viscosity and the dissipation rate. If you plug that estimate of the mean contact duration here, and you carry out the integration with a little bit of algebra, you could show that the transfer velocity must be proportional to the Kolmogorov velocity and proportional to the Schmidt number to the -1/2. Now, Brutes did not put this result as such. He was a little bit impatient as a young scientist who was starting at the time in Cornell. He wanted a useful result very quickly. He actually made the step way early and assumed that the dissipation rate of turbulent kinetic energy is proportional to the mechanical production of turbulent kinetic energy. And he assumed that the mean velocity gradient near the roughness elements scales as U star over the von Karman constant multiplied by the momentum roughness height. And in fact, that gives him the assumption that the dissipation rate is constant with Z. So what he then did is he plugged this estimate here, and with a little bit of algebra showed that the evaporation rate scales with the friction velocity to the 3/4 multiplied by the von Karman constant, the viscosity, the momentum roughness height to the -1/4. Now, of course, one can criticize this result by saying, what about other PDFs of contact durations? Actually, you could show that for the mean evaporation rate, the exact choice of the PDF of contact durations is not too crucial. If you assume a Pareto distribution, if you assume a gamma distribution, if you assume a Wald distribution or a log normal distribution, the first moment is not too sensitive to it. In fact, this constraint is way more important, that the mean contact duration is the Kolmogorov timescale. However, with this scheme, you could derive any statistic of the flux if you want to. You could compute the variance of the flux. And those become very sensitive to the choice of the PDF of contact duration. So as you go to higher moments, of course, they become more important. Okay, another important point from Brutes' derivation was the fact that the average distance that the diffusion front moves into the parcel of air, it can be also estimated. And if you use the same contact duration with the same dependency of that distance on the contact duration, you integrate that result, you find that the distance the diffusion front moves into the air parcels must scale with the Schmidt number to the -1/2 multiplied by the Kolmogorov microscale. And that's a simple algebra. So in fact, the diffusion front is always going to scale with the Schmidt number to the -1/2 in those types of surface renewal schemes where the distance is assumed to scale with the molecular diffusion times the contact duration. And of course, this is nothing but the Batchelor length scale. In fluid mechanics, this is a well-known scale. And often it is assumed that the Batchelor length scale should describe the scalar spectra for Schmidt numbers that are larger than 1. But in fact, in this analysis, for any Schmidt number, you will get that result. Okay, so, and here we are dealing with transport rather than variances. And also the scheme, whether this one or the Lamont-Scott approach, will always predict the Schmidt number to the -1/2, as mentioned before. But there is plenty of evidence for that. If you look at the Schmidt number as a function of the normalized gas transfer velocities, you find that the 1/2 scaling always emerges in this analysis. And of course, these are data sets taken from water because the Schmidt number variations is way bigger in water than in air. In air, it's almost very difficult to get Schmidt numbers much bigger than 1. Okay. Okay. So far, so good. We have shown some interesting connections between work done in hydrology and work done in oceanography. But what is new so far about these approaches? Rather than think about contact durations, we might actually revise our thinking of the gas transfer velocities. What about we think of the gas transfer velocity as related to some turnover velocity rather than contact durations? So that means that if you have an eddy of size r that is spinning, moving mass from the bulk region to the surface or moving mass from the surface into the bulk region, what becomes important for the transfer velocity is how fast this eddy is spinning, which means what is the relative velocity between, or at least in this case I drew it as the vertical velocity, but what is the relative velocity between x and x plus r, where r is the dimension of this eddy. And this is where some closer contact with turbulence theories can be made. You could say that the root mean square value of the transfer velocity, or in this case the velocity difference between these 2 points, can be described by Kolmogorov's theory, adjusted by some viscous cutoff. And in this case, Kolmogorov's theory typically predicts that the spectrum of turbulence scales as -5/3. The spectrum of turbulence simply describes the energy content in eddies, or the structure function simply describes the cumulative energy content in eddies, of size r. And if we then adopt that sort of scaling for the velocity difference across r, then we have that the structure function itself must scale as the dissipation rate to the 2/3 multiplied by the scale of the eddies raised to the 2/3. So the argument here is that it is the root mean square value of the structure function that describes the transfer velocity. So now we have an explicit link between the transfer velocity and eddies. If you plug the structure function expression of Kolmogorov into the transfer velocity, and you do a little bit of simplification, and you further assume, as Brutes has found and others have confirmed by stable isotope, that the most effective eddy that is doing the mixing, or mixing the bulk region with the surface, scales with the Batchelor length scale, then you get, and you assume that this is atmospheric flow, so the Schmidt number is not too big, it's about 1, and the scale therefore becomes the Kolmogorov length scale. You put all these results back in here, and with a little bit of algebra, you find that the result, in fact, for K, scales with the Kolmogorov velocity. So getting that Kolmogorov velocity to describe K is no big deal. It even comes from the wrong spectrum of turbulence, as long as the spectrum is realistic. Brutes actually assumed that the surface is rough, and the reason he assumed the surface is rough was simply due to the fact that the diffusion front of scalars into those eddies is much less than the momentum roughness height where the mean dissipation rate was being evaluated, and that can be now shown automatically from this analysis. Okay, so we recovered the case where the Schmidt number is close to 1, even with the wrong structure function and the wrong spectrum. That mistake cannot be made in the case of water, because the Schmidt number now varies a lot. And so now we need to rethink what to do when the Schmidt number is much bigger than 1. Same idea, now we are moving again from the bulk region, mass to the water surface, and conversely back into the bulk region from the surface. Now Kolmogorov scaling, which is actually shown here, so on the x-axis we have scale, on the y-axis we have the true structure function normalized by the Kolmogorov scaling. So if you have a flat line here, that means that the Kolmogorov scaling holds. And of course now we are dealing with scales much smaller than the Kolmogorov length scale, so the numbers that we are dealing with is in this region. So now we need to figure out a way to describe this shape of the structure function so that we can predict the transfer velocity for water. And that can be done from principles of locally homogeneous and isotropic turbulence, which may not be completely satisfied near interfaces, but hey, let's see where that analysis goes, okay? At least it's a start. It still ties us back to some physics that is connected with the Navier-Stokes equations. And the von Karman-Howard equation basically describes the vortex stretching term, the viscous diffusion terms. Both of those terms are basically receiving the energy transfer, and they simply partition where that energy transfer is going to go. Is it going to go to vortex stretching, or is it going to go to viscous diffusion? And so this is an unclosed equation because you have 2 unknowns, the third order structure function and the second order structure function. If you make the approximation that the cascade is forward, meaning eddies are breaking down and transferring energy to finer and finer eddies, you could then link the third order structure function to the second order structure function through some expressions like this, where the coefficient that is doing this linkage must recover Kolmogorov scaling in the limit of 0 viscosity. So once you do that, you could then solve the von Karman-Howard equation with this sort of simplified approximation. And the outcome of it is that you have a prediction of the structure function normalized by the Kolmogorov structure function, which would be 1 minus this term here that is correcting for viscous effects. And that term turns out to be dependent on a special function that is known as the Dawson function. And the Dawson function is basically like a bump, if you want. Its dependence is on r over theta raised to the 2/3. So of course, as r becomes much smaller than the Kolmogorov length scale, this quantity becomes small. And if you want a 2-term expansion of the Dawson function, let's say this is, so to speak, keeping the major nonlinearity in the Dawson function, you might see that the Dawson function looks something like that. And I should say that if you Fourier transform these results, you explain one of the hotly contested issues in turbulence discussions these days is the so-called bottleneck in the energy spectrum. So on the x-axis is scale, On the y-axis is the energy spectrum multiplied by k to the 5/3. So again, a flat region that is 1 means Kolmogorov scaling. And often than not, both simulations and data seem to show that as the viscous cutoff is being approached, there seems to be a bump or an accumulation of energy near k tau equals 1. So about scales that are just 1 order of magnitude bigger than the Kolmogorov length scale, and then there is the crash. So I should say that this very simplified model that we have proposed, which is shown in blue, explains even this bottleneck. Okay? So there is, it does recover expectations from locally homogeneous anisotropic turbulence. Now, if you plot the two-term expansion of the Dawson function back into the expression and repeat the same algebra, you find that k is square root of 2 over 15. So this number is actually a constant multiplied by the Schmidt number to the -1/2 multiplied by the Kolmogorov velocity. If you evaluate the value of square root of 2 over 15, it turns out to be about 0.36. Recall that Zappa's estimate was 0.41. So now we seem to have an explanation why alpha seems to be so constant across marine or aquatic ecosystems. It seems to be completely driven by locally, at least if this argument is correct, it seems to be driven by locally homogeneous anisotropic turbulence. So now we have shown that we are able to bring the eddies into the description of K. Let's see if we can do a little bit, 2 or 3 more checks, and then I'll stop there. The second check that we have done is the so-called surface divergence methods. These are now quite popular in measuring gas exchanges. The basic premise is that if you put a flotation device and you put a PIV laser under it, so you could measure the vertical velocity just below that flotation device, and if you could measure the position of that flotation, the vertical position of that flotation quite accurately, you could measure the vertical velocity fluctuations at the surface and just below the surface. So you could measure the gradient dWdz squared averaged, basically. And if you use locally isotropic relations, say epsilon is 15 u dWdz squared, this is a well-known result in locally isotropic turbulence, you plug this back in here, you recover the surface divergence results, which means that the constant for the surface divergence approach here is coming from the square root of 215 and this 15, so it turns out that this k is square root of 2 over 15 to the 1/4, which if you evaluate it with a calculator, it turns out to be about 0.71, whereas direct numerical simulations and measurements seem to suggest that this constant is between 0.57 and 0.71. So again, pretty close, okay? Even though the method is quite independent of it. And the surface divergence scheme, of course, is recovered from this scheme simply due to the fact that dWdz is intimately connected to the dissipation. By the way, why is it called surface divergence? Because dWdz is du dx plus dv dy. So in incompressible flow, or as the students like to call it, incomprehensible flow, the dWdz is simply the surface divergence, du dx plus dv dy. Okay, another interesting result is what happens under free convective conditions. So when there is no wind and there is heating, okay? And under those conditions, the dissipation rate itself is given by a mechanical production, but there is also a buoyant production that is dependent on the surface kinematic heat flux, the thermal expansion coefficient, beta naught, which is 1 over temperature for gases, and the gravitational constant. And in fact, that can also be used to formulate the Fox-Richardson number, which is the ratio of mechanical production, the ratio of buoyant production to mechanical production. Richardson had many things in his career. He did weather forecasting, he did turbulence, he was a pacifist, he was a conscientious observer, a Quaker, he was in prison for objecting to participate in World War I, was never allowed to hold a faculty position in the UK. After he discovered that the Royal Air Force was using his studies on dispersion to figure out how to throw chlorine bombs, decided to burn his notes completely. So we don't know what other jewels he must have had hidden under the table when he burned all these notes. And in fact, after that, he decided to move to studies of dynamical systems in the context of why nations wage war against each other. He accused the political establishment of coming up with witty statements in cocktail parties as a form of political debate, and they needed a more rigorous mathematical framework to evaluate policies, and especially when it comes to wars. So he actually was one of the founders of the usage of dynamical systems theories in decisions about wars. So, it's a very, very prolific fellow. So he also had this Richardson number that evaluates the buoyancy term relative to the mechanical production. And in the limit of free convection, of course, the dissipation rate is completely driven by the buoyancy term. And so the transfer velocity itself becomes, based on the formulation that we have just derived, becomes this dissipation rate that is completely driven by convection raised to the 1/4 multiplied by square root of 2/15 multiplied by the Schmidt number to the -1/2. Again, the square root of 2/15 is 0.36. Interesting enough, in an independent study that was derived by Fredrickson using direct numerical simulations of a water surface that is under pure convection, Fredrickson showed that K is proportional to beta naught G Q naught mu to the 1/4. This is actually the thermal production of turbulent kinetic energy. And so again, comparing the 0.36 to the 0.39, it's instructive to show that they were pretty close. Now, to go on a limb as a finishing point, now we are moving away from any rigorous derivation, and it's strictly going to be hand-waving arguments. Okay, so I'm the first to admit that. Okay, but it's instructive to do it. Why is it instructive to do it? Because you could reformulate this equation to read as the dissipation rate multiplied by some turnover time, Tm. When this turnover time is given by the Kolmogorov scaling, you recover all the previous results. However, we can still interpret the energy that is able to transport gas as the dissipation rate multiplied by some turnover velocity with this expression. And if you look at small waves now, not waves that are sufficiently big or might break, just tiny waves, wavelets if you like, yeah, at the surface, their turnover velocity has been predicted by Xanadi from a theoretical argument and some experiments. And their turnover velocity, let's say, time, is of the order of 0.4 multiplied by the viscosity divided by the shear stress squared. Now, if we assume that the dissipation rate scales with the friction velocity cube divided by some thickness delta, and that delta is of the order of 10 multiplied by the viscosity divided by U star, you put all of these together, you find that K must, again, scale with the square root of -1/2 the Schmidt number and the friction velocity. So that's a linear relation with a bunch of coefficients here that are somewhat derivable. Okay. Now, whether this is a fluke or not, it turns out that this number, square root of 2/15, this is very hand-waving, okay? The square root of 2/15 multiplied by 0.4/10, where the 10 came from the thickness of the viscous sublayer, is about 0.073. The data sets that have been published when plotting the gas transfer velocity against friction velocity is of the order of 1/16. So 1/16 is about 0.065 versus 0.073. Although I should be careful giving credit to myself on this derivation because it includes scalars that have nothing to do with transport inside the water. So probably it's a fluke, but it's still instructive to show that it somehow recovers these estimates. Okay, so now to wrap back to the introduction, well, all of this, does this help climate models figure out how to choose A, B, and C? I did not show the answer is yes. You could derive a set of models that do that, but rather than walk through a set of equations, I will walk through the mechanics of the connection that is done between these coefficients, A, B, and C, and how to bring wind speed to K. On the air side, if you have the measured mean velocity at some height, and you have a radiation budget that is giving you, say, the sensible heat flux, you could infer, or modeling the sensible heat flux, you could infer the airside friction velocity and with some approximations such as Charnock's equation or some modification to it that might include wave age or something similar, you could infer basically the airside friction velocity and the amount of heating that goes into the water. Now, if there is no wave breaking, so there is continuity in the spreads, then you could convert the airside friction velocity to a waterside friction velocity based on the density differences. And again, from the same energy balance, you should be able to determine how much heat goes into the water. So now you have the two necessary ingredients that are derived from the airside velocity and models of what's happening at the surface to the waterside part. So in fact, you could link the velocity at some reference height z to K in the water using this approach. And in fact, you could do it analytically. It's just the expressions are a little bit lengthy, so I didn't show them. So to conclude, we started with a result that looks like a resistance law. Yeah? K is F over delta C. This looks like some sort of a conductance, drag, whatever you would like to call it, a resistance law. We've showed that this type of resistance law is somehow connected to the energy content in eddies. So at some level, one might even think of this equality between the two as a form of a fluctuation-dissipation theorem that was developed by Albert Einstein in the studies of the motion of pollen grains by molecular motion. Fluctuation-dissipation theorem, typically what? They relate the drag coefficient to the variance of the random force that is bombarding those pollens, and the correlation time of these bombardments divided by the background kinetic energy that is conserved in the fluctuation-dissipation theorem. In this case, what is really conserved in our system is the dissipation rate, and so that is really the key engine here. However, the idea of linking the integral timescale or some effective timescale that is doing the mixing with the integral timescale that is in the fluctuation-dissipation theorem and the variability in the bombardment of the random force, and here in this case it's vertical velocity, there is quite a bit of analogy, and so perhaps there is some material to be borrowed, so to speak, from the studies of statistical mechanics, specifically in the context of fluctuation-dissipation theorem, to this problem. Okay, so as a final thoughts on where we are going next with this. Of course, we would like to go into more realistic cases, specifically wetlands and emissions from emission of methane from wetlands, which is an important problem. There, the problem is interesting because the diffusion part is only one component. Methane can escape, of course, through the plant directly or through a process that is known as ebullition. Bubbles of methane go from the soil all the way up to the air. And so at this stage, there is no bubbling that has been involved. Everything is primarily diffusing in this thin layer near the surface. And the other phase of the research is, of course, what happens when you have strong winds and wave breaking like that. This has not yet been tackled fully, but there are some thoughts on this. And so with that, I will stop, noting again the famous quotation by George Box, who incidentally I think was at Princeton University, the famous Box and Jenkins in time series analysis. He always actually there's a whole website with quotations by George Box. He said that all models are wrong by definition, otherwise they would not be models, right? But some are useful. So hopefully this was one of them. Thank you.
Questions? Go ahead, you can just call one point you want to get. Go ahead.
So, you say and Brutes that we must affect the scale of the column of the microscopic, but you use an inertial cycle spec. Is that some sort of matching or crossover?
I actually showed the first part of the derivation. For the water, we included the viscous cutoff, but in fact, if you use only the inertial subrange scaling here, right, you get the correct result that the transfer velocity will be proportional to the Kolmogorov velocity, but you get the wrong Schmidt number behavior. If you include the viscous cutoff, you get the right Schmidt number behavior. How is that? Yeah, but even that alone, without the viscous cutoff, will give you the correct relation between the gas transfer velocity and the Kolmogorov velocity, but it will give you the wrong Schmidt number. However, in the atmosphere, it doesn't matter because the Schmidt number is close to unity. You know, gas molecules can move easily between the air molecules. They are so spread apart that the gas has no problems diffusing between the air molecules. But for water, they're tightly packed, and so the diffusion coefficient of many dissolved gases in water is way smaller than the air for that reason. Yes, Amilcar.
So the canopy, when you speak of future steps, the vegetation could move and have a feedback on turbulence. Are you thinking of having that included?
So that was another future topic that I was hesitant to put because that problem now imposes a new vertical dimension on the eddies, and that's an interesting problem, and it's being pursued by many groups. But yes, you could generate wakes. It's just that then the whole machinery of the von Karman-Howard equation is out of the window. However, it may well be that the scaling result here might still hold without the constant, of course. That may still actually hold if the dissipation rate is not distorted too much. If there is short circuiting of the energy cascade and you are adding a lot of wake production that has to be dissipated on top of that, this needs to be rethought a little bit. But if there is no such strong wake production in the waving, it might still actually give a reasonable scaling, let's say, where Tm then will simply be the turnover velocity that may be dependent on the canopy height and the friction velocity, for example. Yeah, Eli.
the viscous sublayer where all this action is happening, instead of these renewals, what we end up seeing are elongated wormholes. And so your theory about this continuous renewal matches better these observations. Is that interpretation right? This kind of continuous turning eddy, which very much looks like these long ones.
I mean, I think the spatial domain that I was thinking about is much bigger than that, in the sense that there is always a renewal event somewhere happening in that domain. Yes, yeah, and so the point is that yes, they always coexist in space, and it's never, you are not going to have a snapshot at a single instant in time where they're not present, let's say, if the domain is big enough.
So my other question is, so this essentially says that bottleneck in the transfer is in the viscous sublayer. Right, so this is the resistance that you should really capture
for gases in water at least, or near rough surfaces. Yeah.
And so then if you have wave breaking or something else, then the fundamentals are changing in terms of what is the right.
Right. Well, so the wave breaking, the first thing that can happen is that the stress is not constant, and the dissipation rate is no longer what's happening in the water side, but what's happening in the wave breaking. And I have to say, I don't have much experience yet. I'm still reading that literature.
You are training bubbles when you...
Of course, and then there is of course the bubble entrainment. Of course, then probably the gas diffusion is the minor part. It'll be all bubbles. Yeah.
What are the prospects for dry air flowing over vegetation being hydrated and therefore becoming buoyant?
So you.
Essentially, to increase the transfer.
So the extra addition of water vapor is dropping the air density and making it lighter, basically. So that actually is a good point. I did not think about this, actually, but that's a very good point, Henry. If I were to make a guess, it will, the Q naught that we have here, let's say, would, in the air side, right, will have both contributions, kinetic temperature and the water vapor fluctuations. So there will be a buoyancy term that will be added to the dissipation rate that is coming from the fluctuations in the water vapor density, because this is really just density. Yeah. If we cut gravity, then this whole term will go away. So here it's not just the surface kinematic heat flux, and there will be the latent heat flux that is associated with it. Or if you like, we can compute the kinematic heat flux based on kinetic temperature or virtual potential temperatures. That will include the water vapor fluctuations as well. So that might actually work. But I don't know how big it's going to be on top of my head in terms of changing dramatically the air density quickly. My limited experience is that it's not a big correction unless you have a huge latent heat flux, meaning bigger than the net radiation that is often arriving at the land surface, which could happen during advective conditions, actually. Yes?
Andy, I was going to ask what happens in the water, but then at the end, you added that. So can I turn my question a little bit about clarification of how you argued this based on that? You understand right, at first you assume that there's a constant diffusion of mass transfer in the water, and that's just constantly let in the air vary. And then at the end you actually let the water actually have turbulence. So you have two turbulent fluids.
Right.
But still the empirical fits, and all the data you show in the first constraint of the first analysis still is water, and it has any turbulence would affect the mass transfer flux in the water, and probably, I don't know if it's linear or exponential or something like that, but which means that is the initial analysis biased based on the assumption that there's a fixed diffusion rate from the water?
That's a very good point. It's not that obvious. So I should go back. Sorry.
That's it.
So this distance is the Kolmogorov length scale, basically. So that's the smallest eddy. So if you have turbulence, that would be its smallest eddy. And if turbulence is going to do anything to bring mass from this bulk concentration without the Schmidt number for a minute to the surface, it will have to be done by this eddy. This is actually the size of the eddy that is most able to interact, if you like, with the viscous sublayer. So if you want to break the viscous sublayer, let's say, and infuse eddies to it, they must be comparable to the thickness of this viscous sublayer, and that would be the Kolmogorov length scale. But you also, in scalars, you have a scalar diffusive layer, because the molecular, at least for water, the molecular diffusion coefficient could be way lower, which means that for the eddies to penetrate the scalar diffusive layer, they must be even smaller than the Kolmogorov length scale. And that's what this effective LB is the length, the Batchelor length scale is simply telling us that these eddies are even smaller than the Kolmogorov microscale. So any extra turbulence that is done here, I mean, these are really tiny distances. We're talking about millimeters, if not 0.1 millimeters and smaller in certain cases, just for reference. So this is really what the scalar analysis is showing, is that your eddies have to be even smaller. And if you look at the energy content in the eddies, it is dropping pretty fast with the drop in scale. So a K41 analysis would be 1, an LB of about factors of 5, maybe smaller than the Kolmogorov microscale, which would be a typical Schmidt number, let's say, of the order of 50, let's say, because it's the square root of that, 25, sorry. Yeah, it'll be somewhere here. So you're dropping your energy content in the effective eddies by a factor of 2 orders of magnitude. But still, it's enough to transfer more efficiently than just pure molecular diffusion, just because this eddy is able to make its way in. It's tiny, but it has some energy.
So does that mean that the empirical analysis that you used in the first part actually is sensitive to that?
The first part, meaning the air side. Yeah.
Air side, yeah.
It's well.
At some, there was the question, how much is it windy or not? You say, oh well, it's windy here.
I think the windy. Yeah. No, it's a good point. The windy part, I think, was coming from the analysis by Zappa that actually showed the agreement between their measured K and the surface renewal predictions. And the measured K had a factor of almost between maybe almost 2 orders of magnitude, let's say, almost. So the question is, what could be generating that? Well, according to this formula, if you are not changing the scalar much, you are changing the dissipation rate. And to change the dissipation rate that much, the U star has to be changing a lot. So that was my point. But the point is well taken. If the velocity is so high, then it's all entrainment of bubbles, and that would be responsible for.
The K you get when you have bubbles are much higher.
Of course, no. I mean, it could be an order of magnitude higher just because of the bubbles. So this is all diffusion. So, and I suspect that at least for the marine ones, I don't know if there was bubbles or not in this particular. These were all for CO2, and SF6 I think was one of them. The rest I'm not sure what sort of scalars they were.
You can see it in the plot in the introduction from Gab, and you have the data for CO2, and they get the K that goes like from 100 to 300 when they are very high wind speed.
Right, I remember that. Yep. I remember that paper. Yeah. So and that was completely due to bubbles. Yeah. So of course, if you start entraining air or you generate bubbles, the story is very different. However, I should say that the way these models are done is that you add the 2 contributions. They're actually additive. So you add the bubble independently of what you get here. There's not a strong interaction between the 2. It's not that the bubble formation impedes the diffusion. It just enhances it according to these models. And so anyhow, these types of approaches need that baseline calculation no matter what, even if you want to do the bubbles.
Maybe we'll take one more question.
I have a quick one. So, Gabi,
Sorry, you missed your chances.
I didn't see another hand.
Okay, go for it then.
Is there another question?
No, it was Samantha moving her hand probably.
So when you have an air-water interface or 2 fluids interface, the resistance that will be the largest is the one where the Schmidt number is the largest. So with air-water, it will be more on the water side. but I mean it's Schmidt to the -1 to the -12. So so can you extend this analysis to kind of looking at transfer velocities on both sides of the interfaces and looking at the whole interface transfer velocity?
You could, and in fact, a lot of models do, because if you're dealing, say, with water vapor, there is nothing resisting from the water side, or heat for that matter. But if you want a single complete model that links air and water, you would want to do that because you want to model water vapor, you want to model heat, and you want to model all the other scalars. But for air, I think it is very difficult to beat the water vapor for soluble, slightly soluble, or sparingly soluble gases. It's almost impossible just because of the packing argument.
Water will dominate.
Water will dominate. So if you were to compute an effective resistance, water will always win over air for CO2 or methane or other gases that you are interested in. It's the water that's going to limit everything. And in the case of the water, if there is bubbles, the bubbles enhance things by factors of 2 to 3 over diffusion, if not more.
On that note, let's thank Gabby again.
Yeah, thanks.